Should we start?
Yes, sir. You can start.
Okay. And the screen is also visible, right?
Yes, yes, yes.
Okay. So if you have any question, you can ask in between as well. So we are discussing about the map reduce. We have seen HDFS, how a large volume of data can be transparently distributed across multiple nodes, right? So like a normal file writing, we will write a file and this HDFS automatically break it into blocks and write it to multiple nodes. And in map reduce, we have seen that how we can write only the map function and reduce function. That map and reduce code will automatically schedule to those nodes where they have the data. They perform the map function on those data, shuffle it. After shuffling, they will perform the reduce function and generate the result. So for example, for frequency calculation, we have seen how efficiently have done this in order of 1. In constant time, we can find the frequency of the words, which is independent of the number of words it present. So ultimately, we HDFS write, split it into multiple nodes, and then we map it that each word is mapped to a value 1. After shuffling, for each word, it will return so many ones, and the reduce basically perform the sum of this to generate the frequency. Now, to understand this map reduce in much better shape, so let us discuss about some other map reduce problems so that we can understand how we can design a map reduce of our own problem. Suppose there are two matrices and we want to add those matrices. But the matrix is very large because we are talking about the big data problem. So as per the volume property, the matrices cannot be loaded in a single node. So we have to distribute it. So first thing that in the split state, we can divide the matrix into rows and each of the rows are distributed across multiple nodes. So suppose the first node got the first two row of the first matrix. The second node got the first two rows of the second matrix. And in the third node, it got the last rows of both the matrices. And then let me show you how can I define the map function and how can I define the reduce function so that this map and reduce function will perform the matrix addition. So what may be the map function? Here my policy is that I will write as a key. So I write the key as a row number. For example, this is the first row that key is 1 and the corresponding values, the first row. And this one is the second row. That's why the key is 2 and this row. Similarly, this map function also parallelly running in node 2. So since this is the first row, this is the second row, it generates key as 1 and 2 and the corresponding rows. And in the third one, since these are the third rows of both, so it generates 3 as the key and the corresponding values. So obviously after shuffling, the reduce will get, wherever there is a 1, the reducer will get 1 and the corresponding rows where the present. So shuffling does that. Similarly, the reduce will get 1 as a key and these two set of values. Similarly, this reduce will get 2 as the key and these two sets of values as the value. And the third reducer will get 3 and this set of values. And now it has become very easy for the reducer to add the element by element to perform the first row, second row, and the third row of all the matrices. So even if your matrices are distributed across thousands of nodes, this map and just write this map function and this reduce function, it will find the resultant addition of the two matrices. So not only you distribute your data, you also parallelize the computation that will perform the matrix addition part. So the previous one is a very simple one to just count the occurrence of that word. This is a little bit higher where we want to perform the element by element addition of the matrices. Now let me discuss about a little bit higher that we want to perform the natural join of two relations. Suppose we have a relation R and relation S, and the records of the relations are distributed across multiple nodes of the HDFS. So suppose R is a relation, these are split. The splits are basically the blocks. So one block has some records, the next block has another records. So you split your relations into multiple blocks of both the schema of both the tables and distribute across multiple nodes. Now the question is, what will be the map function and what will be the reduce function so that we can compute the natural join of the two. So it is quite tough level compared to the previous two. So let me show the tricks that we use here. What it does, if we found, suppose there is a map function, if we found that there is a entry for a relation R, and this is the two values A and B. So if it is from relation R, what we do, this third one is taken as the key, and this two is taken as the value. So this is the mapping we performed. And if it is a record from S, then what we do, this middle one is taken as the key and the rest as the value. So you can see the map previous to example mapping is quite different. But here I apply the tricks that which one should be the key for these two records, right? Once this is done, obviously after shuffling, it will get for that particular B, it will get these two entry wherever they occurs. Not necessarily that it will occurs in the same node, it can occur in any of the node. So after shuffling, they will get that wherever the key occurs, the same set of value will be written here. Once the reducer get it, what it does, it take this one as the first entry, this key as the second entry, and this C as the third entry. And that is the natural join of these two record AB and BC. And that also done parallelly in all the nodes. So it can calculate the natural join so efficiently and so faster. So in the same way, we can see that its complexity will also be very, very less as we increase the number of data nodes in the system to calculate the natural join of that. So not only natural join, any SQL query can be considered in that way to do it efficiently, performing as efficiently SQL query on top of MapReduce. So we understand these three approach: word count approach, next is matrix addition approach, and the third one, given to relation, how we can perform the natural join of these two relations. Now let me discuss about a higher version. So the previous examples, you can see there is a single map followed by a single reduce. So we call it a single pass map reduce implementation. But there are certain applications where a single map, single reduce, you cannot design your application in that way. You may need an iterative version of the map reduce. So the output of the map reduce of one iteration can be given as input to the next iteration of the map reduce. And we can have a loop of such map reduce implementations. So then it becomes quite complicated to do that. So let me show you one example where we need an iterative map reduce, and this problem cannot be solved with a single map and single reduce version. So this example, let us take an example to calculate the page rank. Suppose you are given the directed graph of the web page. So this each vertex are the web page, and each link is basically a hyperlink from page 1 to page 2. Now we want to calculate the popular page. We have to assign the rank to the page. So generally, Google also use this kind of page ranking to assign which one should come once someone search for some records. So how can we perform the page ranking? So first, let me discuss about how a page rank is calculated. There are lots of techniques to calculate the page ranks. So we will use a very simple one, which says that if the probability of reaching a page is higher, the ranks will be higher. So how can I find what is the probability to reach a page? So let us take this example, right? So here there is a page X, and from Y1, Y2, and YM, there is a hyperlink. Now let us see what is the probability to reach X through Y2. So obviously this will be 1 by the outgoing link of Y2. So similarly, X can be reached from Y1. So its probability will be 1 by the outgoing link of Y2. So we can reach X either through this or through Y2 or through YM. So the total probability is the sum. So we can say the sum of all the y from which there is a link to x, the current rank of this y, that is PR of y, into 1 by outgoing link of y. So that is the total probability to reach x through some y. Now someone can directly type this x in the URL and directly reach to that site. So then its probability will be 1 by n. If there are total n number of pages in that link, then the probability that I can type randomly any value, so this is 1 by n. And we can take a weighted average of these two. We can give a weight lambda to this and 1 minus lambda to 1 by n. So in that way, we can say that the page rank of x can be identified by the weighted average of these two components. The first component say that directly I can reach there, and the second one says that I will reach through some links. But here this is a recursive function. The page rank of x is calculated through the page rank of y. So single map and single iteration, single pass cannot do it. So how can I design my map function? How can I design my reduce function so that even if this kind of recursion is there, it can also be solved with a parallel version of the execution, so that very quickly it can converge to the rank of the page. So let me show you the idea of how can we do the rank calculation. So first of all, this graph cannot be represented as an adjacency matrix, right? Because how can I break it? So the idea here is that if we represent this graph as adjacency list means given a web page, we have to find what are the page where there is a hyperlink. So represent this graph as an adjacency list, and this adjacency list are splitted across multiple nodes. So each of the node will get some entry like this, y to this. For example, it is getting only this part. This part is represented by this adjacency list. Now you can see in the calculation, we will do the summation at the reducer. So we have to send this value PRY by outgoing of y to all where they want to perform the reduction. So what we can do that, this value given this y, we can find this value. So we will generate PRY, we will generate this PRY by outgoing y for this y, and for each of them we will take as the key, because I have to give it to them. They will perform the summation at their site, because they need each of them need this value in their summation, because it is going to that x. So we can loop through this part and generate a map taking this x value as the key, and I will calculate my current page rank and its cardinality as the outgoing of y. So that I can perform the mapping. So obviously after shuffling, a node x will get this x as a key, and all the value where there is a page rank, they will come. So that is done by the shuffling part. Once the reducer get this, it recalculate the page rank of x, because already it get those values. So it will use these values as the sum function, and it know the total n and know the parameter lambda. So easily it can find the page rank, updated page rank of x. So previously it was a page rank, now this page rank is updated. Now since the page rank is updated, again the next iteration in a loop, it will send to the mapper and reducer, and that's going on continuously. Finally they will converge, or you can run it continuously so that the page rank will be modified on the fly. If a new link is inserted, new node is inserted, so if there is a loop, we generally call it a web crawler. So using that crawler, it can update. So we can have a map reduce version of the crawler to do it more efficiently. So this is a more complicated version of the map reduce as compared to the previous one. Well, with that, we can conclude that till now, whatever we discuss, it is called the version 1 of the Hadoop. In the version of the Hadoop, they have two versions. One is HDFS that we have discussed. There is some data nodes that stores the blocks of the files, and there is a name node that maintains the mapping of the file to the blocks. That is your HDFS. And on top of HDFS, there is a map reduce. The map reduce does two things. One is called the processing. That processing is done only by two functions. You have to define the map function. You have to define the reduce function. even if single pass or iterative versions that can perform the MapReduce operations. And the second important thing also performed by MapReduce, that is called resource management. So how we decide where the data is there, how to copy this map function to there. So all those things are under resource management. So how MapReduce perform the resource management? By using two softwares, two modules of the MapReduce software. One is called the job tracker, other is called the task tracker. So whenever you put some MapReduce job, like a word count, matrix addition, or it can be page rank calculation. So the job tracker will take this job and it know for that where is the data blocks, because it split it. So the name node, generally job tracker is associated with the name node. The name node can tell where the data present for that job. And accordingly, if it found that one data is present here, one data is present here, one data is present here, it installed or it run this task tracker in these three nodes. So those task tracker basically performs a map function on that data. And once successful, there will be a reduce function where it is goes. So another task tracker will be there to perform that reduce task. So the task tracker is responsible for executing a map task or a reduce task. But the shuffle will be done for all the cases. And the overall execution of the map and reduce task will be managed by the job tracker. So this job tracker and the task tracker, basically the resource management done by MapReduce itself in Hadoop version 1. But in Hadoop version 2, what it does is that the MapReduce is considered as a normal process. But the resource management is given to Yarn. Yarn means yet another resource negotiator. So basically this resource management part is separated. And this MapReduce processing is given as a normal process like others. Along with the other processes, this MapReduce is also running on top of Yarn. So now the Yarn, not necessarily it will run the MapReduce. It can run some other as well. So let me first show that how Yarn perform the resource management. It is much efficient than the previous job tracker, task tracker kind of things that you use in Hadoop version 1. So let us see how in Hadoop version 2, the resource management occurs. So what it does is that there is basically a resource manager. What is a resource manager? The resource manager basically manages the resources of all the nodes in the cluster. So it may be the name node, it may be the data node. So collectively of all the cluster, how many resources are there? What is the status of the resource? So that is managed by the resource manager. So you can install the resource manager in the name node itself or somewhere itself. That is responsible for this management of the overall cluster. And what is node manager? Node manager does the same thing, but it manages the resources only in that node, only for that data node, right? So that's why you can see that the node manager periodically sends it update to the resource manager. All the node manager sent it resource information. Basically, the resource health information is given to them so that the resource manager manage all those things. When a node is down, if there is a failure and there is a map task is going on, so I have to copy the map task to another node manager. So all those things will be done by the resource manager with the help from the node manager they get. And there is an app master. You can see this is the app master. So this app master, you can think about this job tracker, right? For each MapReduce job, there is a job tracker. But here, for each application, because Yarn can manage MapReduce or something else also. So that's why it can be a job tracker, it can be something else. So there is an app master for every application, right? So it will do that. And second thing, what it does, once the client will send a job to the resource manager. Here, the client can be a MapReduce job. The client can be something else, right? If it is a MapReduce, the client will send a MapReduce job to resource manager. Now, what the resource manager does, based on the information from the node manager, it negotiate. Negotiate means how much resource can be provided by a particular node in handshaking with the node manager. So it will, that's why the name is resource negotiator. It will negotiate for the resources that for running that MapReduce job, there is some data. I need so much CPU, so much RAM to do it in that map task or in that reduce task. So that negotiation is done between the resource manager and the node managers. And with that, the app master will update to that the application is started somewhere. And after that, there is a container. based on the negotiated value. For example, suppose one node is negotiated with 2 virtual CPU and 8 GB RAM. So one container will be launched there. So you have to launch some container that I have discussed when I discuss about the cloud computing, right? So the container will be launched wherever I need. For example, in the same node, I may need 2 containers because one container may run one map process, the other container may run another map process on the second kind of data. So you have to decide how many containers needed, where the container to be placed, and that process is basically the resource negotiator kind of things. And with that, once they are completed, once the container completed the task of map or reduce or whatever it is, they report it to the app master. So app master is responsible to collecting the whole result from that container, and it is responsible to give it to the client that the result is done. Once this is done, it will tell the resource manager that the job is completed. So this is the overall flow of managing the resources or running a job with Yarn. And this is much better than the resource management in version 1 of Hadoop that use simple job tracker and task tracker to manage the resources. Well, so now let me discuss about what is the problem of the MapReduce. So hope with that discussion, you have quite understanding of those who already know, they know it, but those to whom this is new concept, you should have some idea that how can we visualize our problem, distributed problem using a map and reduce. So you can say that it's very robust. But what is the problem? The problem is that it cannot be done by a child. It's not a job of a child, right? So with that example, you can understand that with a little bit knowledge of coding, you cannot write a robust and efficient map reduce kind of job. So what it does, it provides lots of supporting tools on top of map reduce to help even a child to write a map reduce job. A child means the beginners of the code that don't have so much confidence on the writing MapReduce code, they can also write a MapReduce on HDFS. So what are they? For example, you see, already we see that HDFS manage the distributed storage. On top of that, there is a Yarn for resource management. And on top of that, we can provide some MapReduce job. That was already there. And you can see lots of supporting tools to help it, to make a novice or beginners to write a code on top of MapReduce. One such tool is called the pig. So basically, I will discuss about this pig and Spark here, and the other tools are providing similar support to do that. So let me discuss about the pig itself. So what a pig is. So pig is an open source platform for big data analysis. How it works? It works is that suppose you have a source of data. You have a source of data. First, the source of data has to be written back to the HDFS, because ultimately for running the MapReduce, I need HDFS platforms where the data is there. Parallelly, I can perform the map and reduce function. So even if it is a streaming also, because the MapReduce and HDFS works on a batch processing. So even if there is a streaming, the streaming data has to be first loaded into the HDFS. And for a particular batch, you have to perform the MapReduce analysis. Another important fact about the pig is that it provides a ETL data pipeline. What is ETL? E for extract, translate, and load. So for example, from that HDFS, you have to write a pig script to extract it. So extract data from the HDFS, transform it to some other form, and again load it. And this cycle will be going on. So this ETL cycle will be continuously going on. That ETL cycle will provide you some analysis of the data it has. If you see the overall flow of the work and the pig is that you have to write your pig script in the pig Latin language, and then using grunt cell or pig server. Once you write your script, there is a parser that will parse your script written by you, and there is an optimizer. Sometimes the script we written in the pig may not be optimum for the MapReduce operations. So the optimizer automatically correct it, modify it, and optimize it, and then compile it to the MapReduce code. So this compiler is the heart of that pig, Apache pig part. So it generates the MapReduce code on behalf of us. We can write our requirement as a scripting in a simple words, and this compiler will generate the MapReduce code, and this execution engine will run this MapReduce code on top of your HDFS cluster. So that is the basic flow of writing the pig script in a pig environment. So that is basically running on top of HDFS clusters. There is a MapReduce, and on top of that we have a pig, and the yarn basically manage the resources. Now let me show you some script. How can I write our script that and how it is easier than the native MapReduce kind of platform. Now the pig has defined some data types, complex data type, apart from the normal integer, float, double, any language supports. So in the pig they have defined 3 complex data types. What are they? The first one is called atom, second one is tuple, third one is bag. Atom is any of the data. For example, we have a string Raja or an integer 30. So all of them are atoms. That is, this cannot be broken down. That's why they are called atom. What is a tuple? The tuple is a collection of such atoms. So tuple can be considered as an entity of a RDBMS, or a row of the table of the RDBMS. And what is a bag? Bag is basically a collection of tuples. So you can consider a bag like a table. So if you see RDBMS table, we have a set of such ordered pairs. So each of the ordered pairs has some ordering of the atoms. So to represent such a database in HDFS, it defines this complex type: atom, tuple, and the bag. Now, let me show you how can I perform a simple analysis using ATAL, that is extract, transform, and load on some raw flat data. Suppose we have a student table, student.txt. Mind that it's not a table, it's just a normal text file. And the text file is huge, right? In that line by line I'm writing, and the total size of the file is such that it cannot be loaded in a single node. So I have to distribute it. And the HDFS basically distribute the blocks of the student.txt files across multiple node itself. Now on top of that, I have to write some pig script to perform some analysis on that student.txt. So first, for extract, transform, and load. Extract will be done by the script called load. So write the load, and that will extract it. So what it does, so load, give the name of the file from where to extract, load student.txt. Now you have to specify, because there is a raw text file, how to know what is the format of that, how to find the individual element for that. So you have to use the pig storage with the regular expression. So this is the regular expression we provide, that comma, so that after reading one line, as per my specified regular expression, it can break it, the first one as a name, the second one as an age, and the third one as a GPA. So I can map these two, name, age, GPA to my each of the record. So that way it will extract all the records from this file and it will load into A. Then it will generate this kind of tuples. So basically after reading, it's generating this tuple using the atoms. Then I will transform it. So so the first step, extract it. Then the first transformation, what I do, I transform this A to B by performing a group by age, right? So it transforms A to B basically. And what is the transformation it applied? Group by. So if I do the group by age, so what it does, it will generate 18 as the, you can see 18 is there, 18 is also there. So 18, there are 2 tuples. 19, there is a 1 tuple. 20, there is a 1 tuple. So this is transforming. Already you have this kind of data. So it is transformed to this. So A is transformed to B. Again, we can transform to another. For example, the B is now, I performing the second transformation to transform to C. What it does, for each B, generate a group and the count of A. So with that, I am finding that 18 and the count is there 2. For example, 19, there is a 1. 20, there is a 1. So I can find for every age how many students are there. So this kind of, I read to transformation. And once this is done, I will perform the store. The store C is a loading. So, so we have, this is E, that is extract. This two is the transform, and finally load. So by using this kind of extract, transform, load, and a series of ETL, I can perform lots of analysis on the data stored in a large-scale distributed file system. So you can see that writing the ETL is much easier compared to writing the MapReduce. But mind that there is a big compiler that internally generate. We write this kind of script here, but it compiled it to the MapReduce. Complex MapReduce is generated there, and ultimately, parallelly, this processing is done, and very quickly this kind of data found. Right. So this finally finding the number of students age-wise, it's complex, but it requires very less time to find it since they are running parallelly using the MapReduce code. So that's why Pig is providing a support to the layman user or the beginners to write the efficient codes that can run in a distributed platform. Another such important thing that helps the beginners to write the code in this kind of distributed platform is called the Spark. So let us see how can I write the Spark code here. So for Spark, already I told you the one problem of the MapReduce is that for each iteration, if there is multiple iteration, after the first iteration of the MapReduce, it write to the HDFS. Then again, it read that file for the next iteration. So there is a bottleneck for writing the disk 2 times. Now Spark solved this because for the first iteration, it read from the HDFS, but the intermediate result, they write it to the in-memory if I want. So it's decision to the programmer. They can decide to cache it in memory, or they can write it back to the HDFS. But if we need a multi-iteration, I will store the output of the first iteration in memory so that the second iteration can directly read it from the memory instead of again reading from the HDFS itself. So this is the advantage of there. Overall architecture, if you see, the Spark is not designed only to help the HDFS. So there is an open-ended source of data which can be analyzed using Spark. For example, HDFS is one of them. Similarly, you can see if your data is directly in the Amazon S3 back in storage, then also you can do it. If you are getting a stream data from IoT device, you can apply Spark for processing. Even if you have a MySQL RDBMS, you can apply Spark for processing on top of that, right? Or data can come from any HPC environment as well. And another advantage is that there is a Spark core that has connectivity to the data source. Then if you want to perform the SQL query kind of streaming, so you have a Spark SQL that use the data frames to perform the analysis using a SQL query kind of structure. And if you want to perform some machine learning, there is a machine learning ML lib and the graphics. On top of that, there is a ML pipeline for the machine learning job. If you want to perform the stream computing, you have to use the Spark streaming. So these are the things given to a programmer to perform the various operations. And for writing the code, there is an open-ended list of programs. You can write this Spark code in Scala, in Java, Python, R, or SQL itself. So this is the overall landscape of the Spark on top of Hadoop. Now, the key concept in Spark is RDD. What is RDD? Like the previous one, we have in case of Pig, you can see that they stored in a particular format, but Spark store it at the format called RDD, or Resilient Distributed Data Set. So let us try to understand what a RDD is of a Spark. Then only you can start writing code on the Spark. So RDD is basically a collection of elements partitions across nodes of a cluster. Now suppose I need data, collection of data. One data is in this HDFS data node. There is another block in this data node, and third block and the fourth block. And I want a data sets considering all those things. So you can define your RDD that will have a mapping there. So mind that this is not copied to there. They are just a pointer kind of things. The data is there itself, but you can define the RDD to point to that. So RDD defined that these are the collection of data. Now, this will help writing the Spark script in some better way. So now if you see that the peak works as a ETL format, that is extract, transform, and load. But your Spark works in that format. What it does, first you have to create some parent, RDD, and you have to apply some transformation on that RDD. So you take on RDD, perform some transformation, generate another RDD, and there is a circle of transformations. So this parent RDD is similar to some extraction and this transformation. And finally, load is quite similar to the action. It says that on the final RDD, you have to take some action to generate a result. So first you have to define your starting RDD or the parent RDD. On that parent RDD, apply lots of transformations similar to the peak. And on the final RDD, apply some action to get some insights on the data or some result. Now, what are the transformation? What are the actions available? So some of the transformation you can see map. So the default is you can see the map or the map partition, flip map, filter, sort by key, reduce by key or group by key. So you can see only this map and reduce is one thing. But Spark can be applied for all others. Lots of transformation is there, not only map reduce. So if I want to do map reduce, I have to apply map transformation, reduce transformation. Only one use case. But the others can also be applied to work with the Spark. So similarly, union, join, Cartesian product kind of things. Now, what are the action available? The action also you can perform reduce, you can find count, you can perform for each, save, collect. So lots of action can be taken. Now, to understand how this transformation and how these actions can be applied, let me show you one example. For example, suppose there is a log file. There is a some computation is going there, and the resultant log is written to the HDFS. So in the Spark context, first get a context of the Spark reference value. This Spark context dot just call text file, and the source is a HDFS file. The name node reference to the HDFS file name. So that will find where the blocks are there, and automatically it will create RDD. So we create a log RDD. So ultimately data is not moving. From that HDFS file, it know the name node say where the blocks of the files are there, and using that pointer, it creates a log RDD kind of things. So now this log RDD becomes our parent RDD. Now on this parent RDD, what I does, I have to apply some transformation. What transformation I apply? So I take this log RDD and I apply the transformation as filter. You can see there is a filter. So I apply this filter and I check if a particular line contains error. So this kind of filter you can specify, and it will generate another RDD called errors RDD, because RDDs are immutable. You cannot modify RDD because RDD has some simple reference, one-way reference. You cannot go to the outwards to update it. So from one RDD, you can generate another RDD. So from there, wherever this present, so there will be another pointers. You can create a errors RDD. So this can be considered as extract. It can be considered transform. And finally, you can apply some action. So for example, within that, I have to find how many logs records are there containing errors. Or we can say how many errors occurs. So in that way, starting from a parent RDD, by applying lots of transformation and finally applying the action, we can have some analysis on data itself, where the data is inherently stored in a large-scale distributed platform. Now,
Sir,
yeah.
Sorry to interrupt, sir. Probably there is a question from Dr. Kaushik Mondal.
Yeah. So, can you tell me?
Sir, you have raised your hand, so yes, sir. You may proceed. Sir, if you have any query, please ask.
Okay, so then at the end, we can also take the question. So in between, if you have, so just unmute and ask me, no issue. Okay, so we understand the difference between a peak and Spark, and both has a similar policy. We have to extract, then we have to transform something. Finally, we have to load it. So in the peak, they have different nomenclature. And in case of Spark, we have different nomenclature, but the policy is quite similar. So there is, if you see how efficient it is, so let us keep the sum of the transformations. So these are some theoreticals. So we can remove the slides. So now let me show you the same word count problem that we apply the map radius, how easily it can be done in the Spark. So for example, suppose there is an input file. So just from that Spark context called text file, and this is the input file. So that will get your parent RDD. So lines is your parent RDD. Now I apply transformation. On that lines, first transformation I apply is a flat map. How to perform the flat map? I specify in a lambda function. What I do, simply split it. That means in that lines, how many words are there? All the words are split. That is tokenized. So by this transformation is tokenize the word. Then what is the resultant value? See, there is a cascading of transformation. The second transformation I apply as a map. What the map does? Whatever the output I get from here for each word, I generate a map of word comma one. So this is the map. Word becomes the key and one becomes the value. And then I perform the next transformation called reduce by key. That is for two records X and Y, if their key are same, then perform the addition on that. And finally, whatever the RDD found, it assigned to the word counts. So only three, I just apply three transformation. So I have a parent RDD followed by three transformations on that RDD. And from that final RDD, I apply that action collect. So if I apply this action collect, we will get the result. And from there, I can print for each result what is the word. Now look at this, how easy it is. But internally, it is generating the same MapReduce code that I have shown you in the very beginning. But here, you do not need to write any map code. You do not need to write any reduce code. Just define who is the parent RDD, what are the transformation to be applied on that parent RDD, and finally, how to collect the result by applying some action on that. So you can see the MapReduce becomes so easy with the Spark context, right? So that's why that if you were efficient one, you can directly write your MapReduce on top of HDFS. And if you are not confident on the MapReduce programming aspects, either you can use the PIG or Spark. The Spark becomes very popular due to a rich set of transformations and the actions to be applied there. And the second thing is that PIG can be applied only on top of MapReduce, but the Spark can be applied to any context. Not necessarily I have to get the data from the HDFS. From any IoT devices, the data is coming, I can map it to RDD and perform some transformation and get the result. So stream computing becomes very easy with the Spark. Well, so now finally, at the last topic, the topic was that the machine learning as a service. So let me now discuss about what a machine learning is or what is the data science. Till now, I have discussed about the big data. The data has big volume. They have some variety, veracity, volume property, lots of things, but they are not the data science. So what is the data science? So all of you know about probably better than me what a machine learning and data science is. But I want to show one thing, one thing is there that the Gartner told that the data is the well of 21st century. But the fact is that data is a crude well. It's not the well. That is, we have to mine it. So who will mine it? The data scientists. So we need some data scientists who will apply some data science algorithms to get some insight from the crude well of the data. Now there is I find it very interesting from there that we need these three things for performing the data science. One is we should have some knowledge of the mathematics and statistics. We should have a knowledge of hacking the systems, hacking the math, and we should have a domain knowledge. If you see, if you can hack to the math and statistics, you are landing to the machine learning space. And if a hacker, if someone which has a very good domain knowledge and he applied that math and statistics, they are doing some traditional research. And if you merge all these three, look at the data science space here. You know the math and statistics. You know how to hack this math and statistics for that. And you know how to apply it in a particular domain. Then only you becomes a data science. And there is a danger zone. If you hack it and you have a domain knowledge, but you don't know math and statistics, it's a very dangerous thing. So the thing is that main thing, you should need to hack something to the math to land off in a data science with the knowledge of the problem you're solving. You know, those who are working on the machine learning, they don't have the domain knowledge. If you see our students, if you give our students some problems, so whatever the model they take, if you give in another domain, there is no problem. The same thing occurs because they have some multiple layers, input layer, hidden layers, output layers. They give some data to train it. But if you ask him that instead of this domain, if I apply your model to other domains, will it be different? There is no answer because they don't know the domain knowledge itself. They are not domain expertise. So that's why they are ended up in machine learning. But to become a data scientist, they must have, along with that concept, they must have the domain expertise that this model exactly performed properly for that domain and why. They can explain it, why they are getting this kind of result. So to become a data scientist, we need a hacking skill that can hack to the mathematics, and we should have a domain knowledge, this kind of things. So now let me show you that how this hacking and math related to each other. So let me explain how we can perform the hacking to the mathematics in the context of gradient descent, right? Suppose we all know about the gradient descent algorithm, right? There is a forward pass and the backward pass that can train some weight of a neural network. So let us take an example. There is a 4-layer convolutional neural network. There is a first layer, the input layer, 2 hidden layers, and 1 output layer. And these are the features. So we give the features as x1, x2 up to xd. D-dimension features is given to the input. And finally, the forward pass and the backward pass, they try to find the weight of that leads because you don't know the weight. We have to learn the weight. And this weight is unknown to me. Now let us see what is the math and how we are hacking to that math. So what we does basically, first, you can see you are given some set of training data. So training data means these are the features and these are the label. So label data is given that if this is the features value, then this is the class of that. Now, given this, with that, we can find the finally activation, AK. So obviously, my requirement was TN and we are ending up with AK. So there is an error of TK minus AK. And the mean square error, we can compute as equal to half of sum of all the errors for all these layers, right? Now, for doing that, what I need to know, we have to find that given a particular weight vector, so we can end up with a particular error value. So we need to find for which weight vector. So we need to find this weight that minimize this error, right? Optimal error. And for that, we need to find that gradient because this error curve is like that. So we need to find the gradient. Using that gradient, we have to find what is the minimum point. So let us see the math behind this, how it works. So you can see that at the activation level, before applying that activation, we find the net value. So suppose there is activation of the previous stage AJ and there is activation AK. So if there is a AJ and this one is the kth node, so we call this weight as WKJ. WKJ is this weight. So what we does, we have this activation into this weight, similarly this activation into this weight. So we have WKJ into AJ, the sum over J equal to 1 to the hidden nodes. So many hidden nodes are there. So sum over this to find the net value here. Once we get the net value, we can apply that sigmoid function for the activation. So the AK will be 1 by 1 plus e to the power minus net k. So this kind of sigmoid we applied here. Now, the hacking related to here is that how can we perform this derivative, or how can I measure the gradient of delta E by delta W? That directly we can do that. But by hacking that system, we can find out it. How we hack it? First, we calculate delta E by delta. So here the things first I found, because already I know this E function, and relative to AK, I want to perform it. So if you perform that derivative, so clearly for all other terms other than AK, they will be vanished. So the sum terms is removed and becomes only one terms, that is related to kth term. And with that, by simple derivative, we get minus tk minus ak. Once I get this, the next derivation we can find that the derivative of ak relative to this net k value. Already we have this net k function. So if we apply this, easily we can find out the value to be a very handsome kind of value, ak into 1 minus ak. And again, if we apply net k by wkj, we find it to be ak. And then we can find that the derivative of E with respect to that wkj adds the multiplication of these three derivatives, and we come up with a very good result. And here is a hacking. A hacker hacked the mathematics to find this derivative indirectly. And your W, you know, it's a vector. So we can update it, that giving that current value, we can update it by multiplying with the learning rate to the sum of all these values, right? So that way we can hack to the mathematics systems to perform some machine learning. So that's come up to the machine learning, because we don't know any domain knowledge. This is common for all the domains. Whenever we apply it for that specific domain, it becomes a data science itself. But what I am interested here is that how can we apply the map reduce to calculate this? So from there we can see there is a summation. So that can be done by a reduce function. And this can be find out by the map. So easily we can do the mapping that wherever they have this data, that is TK, AK, and AJ, wherever this data is there, they will perform the map function where the key will be WKJ and the value will be this, because they have this three value, they can calculate this value. And after shuffling, they will get wherever they need WKJ related to that, all this value will be come to the common place. So the reduce function will perform that summation. This alpha is a learning rate that is common to all. They apply this and they can update it. Now using this iterative map reduce, it will converge and finally it will find in a very quick way. So if we perform that batch gradient descent in the map reduce version, you can converge to the optimal solutions of the weights very quickly compared to the sequential or a centralized solution of the batch gradient descent kind of things. So that is an idea of how MapReduce can be used there in the field of machine learning or the data science itself. So there is another example for k-means clustering in the same way. So due to the shortage of time, I am skipping those things. So you can see that if your data is distributed, how can I find the k-means cluster? Because for finding the k-means, if you see here, you need all the data, then only you can find the cluster center. But your data is distributed. You can see the data 1 is in one node, data dn is another node. So how can we find the centroids there? So here the idea here is that you can have a global centroid and the map function. You can see the map function first load the global centroid. Now based on the current value they have, they can find the closest centroid from the global in the previous iteration, and then they can generate a map that this point should belongs to the new closest centroid as per the previous round. Now after shuffling for a particular centroid, all the points that are mapped in that iteration to that centroid come to the same place. So to the reduce, the key is a centroid and all the values who are mapped to them. So this mapping can be done in any of the nodes, but after shuffling they come to the common node, so they can find the new centroid and they can emit that for this centroid, this is the new value which will update this global centroid there. So this is a map reduced version to find the k-means clustering. So if your data is huge, the clustering itself takes a long time, so you can use this kind of logic to do that. Now at the end of that, I will show you the machine learning as a service. So I want to use Amazon AWS, that how those things I can use as a service, so that I will not bother about all those complex things. I will give my machine learning training, testing, and all those tasks, and it will do it on behalf of me. Before going to that, if anyone has any question, because technical discussion is over, I will demonstrate basically. I will log into the AWS and I will show you that how you can perform some machine learning as a service there. So if anyone have any technical questions on the discussion that I have done today.
Participants, if you're having any question, please raise your hand. So no one has raised their any.
Okay.
Okay.
Okay, so let me now demonstrate this. The second topic was that machine learning as a service. So ultimately, there are lots of service. We can use the cloud, Google service or Colab service. Lots of services are there. I will demonstrate for Amazon Web Service, AWS. Now, Amazon has their own data centers. So either using command prompt, you can log into that, or you can have some SDK to write your program to connect it, or through the web, you can log into that system. So ultimately, they provide few infrastructure service that I will use for our machine learning part. One service is called EC2, Elastic Compute Cloud. The other one is the EBS. And the third one is S3 or Simple Storage Service. And EBS is Elastic Block Storage. What are they? So the EC2 basically help you provide some virtual machine, right? On the Google, on the Amazon servers. So using EC2, you can launch some virtual machine and you can launch some elastic block storage. So elastic block storage are the hard disk that can be mounted to any virtual machine. So using that EVS, you can create a virtual disk or virtual hard disk, and that can be mounted to any of the nodes. So you mount that virtual disk to that virtual machine so that whatever processing work on there, the result will be stored in the EBS. So your data will be generated in the EBS itself. Now you can unmount it and mount it to any others. So the data transfer between two nodes becomes very easy. Connect it to one of the node, create some data, and just connect to the second node. Its data is available to the second node itself. And not only that, from EBS, you can create a zipped version called a snapshot. And from that snapshot, any number of EBS you can create. So whatever the last state of the EBS, it will be copied to that newly launched EBS. And that can be mounted separately to the VMs. So using EBS and snapshot, this kind of operation you can do. And S3 is basically archive data. So for large volume of data, for basically for machine learning, most of the time, we will store the training data set in the S3. So S3 cannot be mounted. S3 is the backend. So whenever I want to perform some analysis, from S3, I have to load it to some EBS, and then I will perform some analysis on that. That is the basic workflow and the infrastructure service needed or provided in the AWS. And for the platforms, if you have some RDBMS, if you need some RDBMS with SQL query, you can use the RDS service, relational data store. And if you have a unstructured data or semi-structured data, you have to use DynamoDB. And if you want to perform some Hadoop operations, so the Hadoop is implemented, whatever I discuss about the MapReduce and your HDFS, so they are implemented as EMR. So EMR is Elastic MapReduce. So if you want to use the MapReduce operation, so use that services from the EMR. So there is an example that how you can use the AWS data pipeline on top of EMR. Suppose you have a EC2, the normal virtual machine. So daily transaction is going on. So daily transaction at the end of the day, you are exporting to the S3. So the S3 for everyday transactions are loaded there. And the end of the week, you can launch a EMR cluster, MapReduce cluster, that will get the data from that S3 loaded into that EMR or the HDFS inside the EMR, and then you can perform some MapReduce jobs to get inside. And this pipeline can be working continuously. So this EMR also provide a good service for big data analytics over AWS platform. Now, if you see the machine learning, let me see what are the tools available in AWS for machine learning process. We all know that these are the overall flow for machine learning operation. Suppose you are given a business problem. So first thing you have to transform into the machine learning problem. So there we need a domain experts. If you have a domain knowledge, then only that particular business problem can be converted to a machine learning problem. Once you do this, the next task is that you have to collect the data. So the data collection, data integration, data preparation, cleaning, we call it a data pre-processing collectively, has to be done, followed by data visualization and analysis. So just analyze and visualize it so that we can find some understanding of the data they have. Once we have, we perform the feature engineering. Right? If the feature engineering we want to, if we use the deep neural network, then the feature engineering can be a part of that as well. So after feature engineering, we have to train the model and tune the parameters, and then we have to evaluate the model. Satisfied with that, due to the low number of features, the next thing we will try is that can we augment some features? We can add some extra features to that data itself. We are not adding the data from the data itself. We are extracting more features. So that is called the feature augmentation. And then do the same thing. If it are still not satisfied, then we have to perform the data augmentation. In the current data, we cannot do this. Add more data so that more features can be done. We can do this. And this cycle will be going on. Once we are satisfied, then our model is trained. The model has to be deployed. Then we have performed some predictions and inference on that. And finally, we are done. So this cycle, they provide as a one-stop solutions as a services by Amazon. And this service, they provide like by a service called SageMaker. AWS SageMaker is a tool that provides this full flow of the machine learning jobs that I discussed in the previous slide. So what they do, this is your client application. Now you need a container. Already I talked about the container part, right? So in a container registry, they already have some training code. That is the machine learning training code is already you have written and stored into that ECR. So already some for standard machine learning problems, some training code is already there. You can write your own code as well. And then you have to put your training data in an Amazon S3, simple storage service. And there is a, you have to launch a EC2 instance with the helper code that will take this training code here and your training data there and perform that model. With that, it will generate the model and store the model artifacts again in S3. Now for inference, for doing some inference on that model, again, you should have some inference code there, or you can write your own inference. And based on that, there is a helper code that will take this model, this inference code is there, and it will generate an inference endpoint. Once it generates the inference endpoint, the client will send some request, that is the query, data analysis query, and it will return that result back to the client. You can perform some data analysis on that. So in that way, it does the data analysis there. So let me show you a simple analysis in Amazon SageMaker. In Amazon EC2 AWS. So let me log into Amazon EC2. Can I go there? So there is the things that I already log into that Amazon EC2 because it takes some time. So once you log into your AWS console, if you go to that services, you can see lots of services they already provide. There is a compute service. So in the compute, I show you the EC2. So if you go to the EC2 service, you can see the instances. The instances means the virtual machine. You can see some EBS, S3, all those things are under this services part. Now, due to the shortage of time, I'm not going to discuss about those things. So let me go to the machine learning part. Under the services, if you go to, there is a tab called machine learning. Just click on machine learning part here. So just click on machine learning. You can see lots of machine learning tools provided by Amazon EC2 for different operation. And we are interested in Amazon SageMaker. So go to the bottom, you can see there is an Amazon SageMaker AI. So this Amazon SageMaker AI, if you see, it is used to build, train, and deploy machine learning models there. So since we want to use the machine learning as a service, so we have to use Amazon SageMaker AI tool. So if you click on that Amazon SageMaker AI tool, so let's see what we get there. So actually it's time consuming because it is going to Amazon US. Okay. So once you go to the Amazon SageMaker, first thing you need is the notebook. So you have to click on the notebook. It is too slow. So click on the notebooks. So like a Jupyter notebook kind of things, where we will write our machine learning code. So already I have created one notebook. I will show you that using that notebook, how can we write this code. So in that notebook, so you can see I have already created my notebook that is in service, and we can open the Jupyter or Jupyter Lab. So let's click on the Open Jupyter. It will open your Jupyter notebook. But mind that this code will be running in the Amazon cloud itself. So if you go for Google Colab, so you don't have the control on the exact instances where it will run. So you can provide this kind of control with this notebook in AWS. I don't know, due to the network issue, it's taking a long time. Kamalesh is there?
Yes, sir.
Kamalesh?
Yes, sir. Sir, am I audible?
So is this due to so many participants are there due to that network issue? It's taking generally more time than the user.
Sir,
Anyway, maybe. So anyway, so now it opened that Jupyter notebook that is running in the EC2 itself. If you click on that notebook, so it will give you this. So you can see already I have so many things. Let me not to run them because just few minutes back I used this. So you can see I perform some linear regression on that. So like normal notebook you are doing, so just write it, the code, and you can finding all those things. You can see that this regression model also, it is running inside my EC2 instances. Now, if I have a huge data, training data, so then I will store my data in the S3 instead of there. Here I generate my own training data, training and testing data. So by using some randomization. But I can easily write in the notebook that I can map it to the S3 so that it will take the data from the S3. And second thing, that notebook is associated with the corresponding instance type. I can increase, if my data size is very, very high, very, very large, I can increase this instance to a higher value that the training can be done at a much lesser time. So generally our student complain that it takes 2-3 days to complete in a collab. So we can go for this SageMaker and we can assign some large instance. So you can perform the training in a much lesser time. So I think with that, I will stop here if there is any question.
Participants, do you have any question? Please raise your hand. It was a very informative session indeed, and more than 240 participants throughout the session. Okay, Dr. Shottobruto Maiti, please unmute yourself and
Well, sir, good evening, and this was indeed a very good lecture.
Thank
Uh,
you.
sir, actually, I would like to ask you two, three things. One thing is there any cost included with this when we are using this cloud service?
Yeah, because you have to use that S3, there is a cost.
Mhm.
For data transmission from S3 to EC2, there is a cost associated. And
Okay.
the Amazon, the SafeGuard also SafeMaker also takes some cost. So if you go to the Amazon EC2 pricing, they have a details breakup of the cost structure because the cost is
Okay.
variable. What kind of instance we use for the training,
Okay.
the cost also depend on that. But they have a good calculator to calculate that
Mhm.
if I run it in a particular instance type and this is my data size, what will be the
Okay.
cost?
Understood, sir. And one more thing, can we connect that map reducer, what you have explained just before this example, with this EC2? EC,
No. For that, Amazon provide EMR, Elastic Map Reduce.
okay.
So if I want to perform that Hadoop map reduce, we have to go for EMR.
And we can actually, after all the training done, we
Mhm.
can download the machine and we can use it somewhere else.
Yeah, data after the analysis, the data is stored in the S3. So
Okay,
S3 is cost of the S3 is less. So if
understood.
you terminate your cluster, you store
Mhm.
your data there itself. Anytime you can download it to your local system, the results.
Understood, sir. Understood, sir. Thank you so much.
Okay.
So what is the difference between S3 and EBS, Elastic Block Storage? Actually,
So EBS is your virtual disk that can be mounted to any instance. But S3 is an archival data, like a warehouse kind of things. So that cannot be mounted to any instance. So if you store your data in S3 and from your virtual machine you want to access it, first you have to download from S3 to a EBS because the instance can directly access only the EBS, not the S3. Is that clear?
um, the VM cannot access the S3 data.
You
Hello.
have to download it. S3 has a URL. From that instance, you can download. So whenever you download, that will be loaded to the EBS part. But if a data is in the S3, you cannot write a program that will directly access this S3 itself. But if you load your data in a EBS, a particular file can be mapped or mounted directly to the instance. So the technical term is that we can mount EBS to the instance, but S3 cannot be mounted. S3 has to be downloaded, right? So that's why if
Okay.
your S3 and the instance are in the same zone, the network cost is less. But if your S3 is in one zone,
S3 is for static storage, right? Means simply storing some files, etc. and
exactly, there is
accessing it.
some bucket. There is some bucket. In the bucket, you would just store some data, and that provide a URL. So from that URL, you can download there. But the EBS basically can be directly associated with the instances.
Okay.
Sir, in this screen, the calculation or splitting is shown. One sample splitting is there. Like for
Mhm.
different services, the cost will be different for different components. So which service is being used as much, how much it is being used, based on that, this price or bill for that month will be generated.
And the tax will be for that where it is launched, right? Not locally where it will use.
That will be based on this zone.
Zone,
Here it
right?
is global, but based on that zone, in which
Yes,
area, in which data center it is being deployed, based on that tax will be calculated.
exactly.
Dr. Shiladitya Munshi sir, our very own Shilada. Shilada, please unmute yourself.
Am I audible?
Yeah, yeah.
Yes, no, yeah.
Okay. Good evening, sir. So I have a very generic sort of question, but not related with this AWS, but rather it is quite related with the previous session. I couldn't
Yeah.
ask that time. That right now we are living on the real-time processing kind of thing, right? So in the realm of
Your
real
voice is breaking.
time processing, how this Hadoop batch processing system can work? I mean, what is the implication of this batch processing, or how can we manage this batch processing in the real-time scenario?
Oh, so you are talking about that the batch processing of Hadoop is a problem, right?
Yes, sir, because Hadoop is all about batch processing, right?
Yeah, yeah. MapReduce will work on the batch processing. That's why I
So
told
in
you
this
that.
age of real time processing, how come this batch processing scenario work?
Yeah, that's why in that case we have to use the Spark kind of things that provide you streaming operations. So Spark on top of Hadoop will provide you a real-time operation using the streaming access. So in MapReduce you cannot do the
Okay,
streaming.
so can we think of the micro batch kind of thing?
Yeah, that you can do. That I told you that I will store the stream in the HDFS. I perform on that mini batch. In the next streaming comes. So you have to do it manually. But if you use the streaming features of the Spark, that will do it automatically.
Okay, I understood, sir. Thank you very much, sir.
So I think we have almost concluded the session. Thank you very much, sir, for this wonderful presentation. And thank you to the participants for this patience hearing. Maybe some few of you are having some network issues, but anyhow, it's managed. So may I now request participants to quickly switch on their video so that we can have a click few pictures. Participants, please quickly switch on your video. Just give me 1-2 more minutes. Okay, done. So thank you, participants. So tomorrow again, 6 o'clock. Thank you very much again, Katua sir. Nothing to say much to you. I don't know. I have no words to thank you much.
My thanks also to you and your organizing committee for arranging such a nice. Okay, so I'm leaving.
Okay, sir. Thank you. Good night.
Good night.
Participants, you can leave too, but I'm sharing the feedback link of session 6. So please fill with your registered mail ID, and along with that, complete the process within 11:59 p.m. tonight. It will be very helpful for us to manage everything in the next day morning, because so many participants are there. So please follow that, because next day it's tough for us to manage everything. So please complete the process with your registered mail ID and within 11:59 p.m. tonight. Thank you very much. Good night, everyone. Kamala sir, you can end the meeting.